Good evening, everyone. This is Celso Battaglia, Astronomy 10, Evergreen Valley College. And today is a continuation of what we covered yesterday. And we are pretty much going over details of our only star, the star in our solar system, that is the Sun. So yesterday we saw the Sun in its atmosphere and interior part, and we discussed uh, what were the basic differences between those interior and exterior regions. So the sun's in its interior part, in the very core, has a furnace where nuclear reactions are taking place and igniting the sun. So if we think about the sun as a source of energy, this energy comes from the central part, the core itself, and then it propagates through the radiative diffusive shell, and then it hits the convective zone where mass material moves outward, carrying heat to the outer regions of the solar interior, which coincides with the lower regions of the sun's atmosphere. So the sun atmosphere, in its turn, is divided in three main regions: photosphere, chromosphere, and corona. And in the photosphere, we saw the onset of several bubbles, convective cells. They are they are called granulations, and these granulations is a few percentage, or three quarters or so, half size of our own planet Earth. And then the chromosphere is a region where the temperature rise. We didn't go in details as to why this happens. As you go from the central part to the outer regions of the sun, the temperature drops from millions of Kelvin in the very core to a few thousand Kelvins in its exterior part. But eventually, in the chromosphere, the temperature rises up again as a result of transfer of energy, in fact, magnetic acoustic energy that is generated in the solar interior that passes through the photosphere and dissipates in the chromosphere and corona, and giving rise to this phenomenal display of um, light gas in the corona, um, with with a somewhat fantastic production of X-rays. So today, continuing with the sun, I would like to focus on the aspect of the sun that has to do with activity. And as always, I would like to remind you we have a discussion going on exoplanets, and tomorrow I will do my first survey of reading on the discussions that have been posted and graded. And the discussion is, well, in our solar system, the terrestrial planets, those closer to the sun, they are rocky type, and they are small, they don't have a lot of satellites, and they don't rotate fast, and they are depleted of volatiles. And when you look at the gas giant planets, the Jovian planets, on the contrary, they have a larger percentage of volatiles. They have a large number of satellites. They rotate fast. They have strong magnetic fields. So why? So we should expect that in stars out there, based on what we see in our solar system, we would expect that Jupiter-sized planets would be found far away from the star. And yet, the first campaign to detect exoplanets using radio velocity techniques or Doppler effect, it found a large number of planets closer to the star, and these planets were Jupiter-sized. So how is that possible? So we know in our solar system, Jupiter-sized planets could not be formed close to the star, or their volatiles would evaporate, would be casted away. So how come in these exo worlds we find exoplanets, Jupiter-sized, closer to the star. So what's going on here? That's the point of discussion, and you have to provide a good answer to that. And we have the homework based on our sun as a star. So I would like to initiate with the video. It's a short video about the sun.
Hello and welcome. I'm Jane Houston Jones at
That's the
NASA's Jet Propulsion
granulations
Laboratory in Pasadena,
and
California.
prominence. So
2009
as you can see, it's an
International
old
Year of
video,
Astronomy.
but it's
Each
interesting.
month this year, we'll take you on a tour of one of the best celestial objects on view. This month, it's our star, the Sun. Galileo and Englishman Thomas Harriot both observed the Sun and sunspots in 1610, but they weren't the first. Chinese and Korean astronomers wrote about sunspots almost 3,000 years ago.
Probably all these Chinese and Korean astronomers observing the sun 3,000 years ago, they had a short life as astronomers because they probably got blind in no time. You should not stare at the sun. Please do never ever do that because it affects your retina and causes major damage to the lens system of your eyes.
John of Worcester, who was an English monk, made the earliest existing drawings of sunspots in 1128. Galileo's solar observations of 1612 were made at the same time of the day every day, and so the motion of the spots across the sun can easily be seen. This motion allowed early astronomers to estimate the sun's rotation period, which is about 27 days. The early astronomers soon projected the sun's image through the telescope onto a piece of paper or through a pinhole projector. This made it possible to study the sun in detail without damaging their eyes. Many other astronomers in the 17th century, including Scheiner, Gassendi, and Hevelius, also recorded their solar observations. More than 24 past and present NASA missions explore the Sun-Earth system. The Ulysses spacecraft, which launched in 1990, studied the Sun before, during, and after the last solar maximum in 2001. After more than 18 years in flight, Ulysses returned a wealth of data that led to a much broader understanding of the global structure of the Sun's environment. The TRACE spacecraft launched in 1998, and it studies the magnetic structures which emerge through the photosphere.
Interesting. I was going to stop here just to show, which is point of today's class, is the sun's magnetic activity. So these traces or these lines you're seeing here is in fact lines of magnetic field lines. Just a second, let me do something here. They are lines of magnetic field, and these magnetic fields in the sun are generated as the result of moving charges. So the sun is hot, and then the atoms lose their the atoms lose their ions. Just a second, I have to. My family is well, sorry about that. That's going to be popping up. I'm not going to pay attention. But
the Genesis spacecraft.
These magnetic field lines generated by the fact that the sun has atoms, and these atoms, as a result of the high temperature, they lose electrons, and now you have these charged particles, electrons and ions, circulating the sun as a result of the solar rotation, and as I mentioned yesterday, the sun's convective bubbling up convective zone. So as a result of this mass motion of ions, magnetic fields are generated. When we study physics, we learn that magnetic fields can be generated when ions move, when ions have circulations and motion. So this global magnetic field the sun has is generated by the sun itself, motion associated with the particles. And what you saw in this
The
display
Genesis, much broader understanding, launched
over
in
here,
1998.
right here,
and
is a bunch of magnetic field lines, and they have the properties of freezing ions in it, like beads attached to a string, making a necklace. So you have these field lines that raise and erupt off the solar atmosphere, and attached to them, you have a string of particles that move, guided it themselves by the sun's magnetic field. And when these magnetic fields concentrate in certain regions, it raises up the temperature of that region, because now you're forcing the particles to be close to one another, and nature reacts with mobility and collisions when some external forces try to confine the particles. So hot regions in the solar atmosphere are associated with concentration of magnetic fields. Cold regions in the solar atmosphere, which are sunspots, they are cold regions, are also associated with the presence of a strong magnetic field, because in the regions where the spots are located, the magnetic field is so intense that prevents the heating up process produced by the convective motions in the subsurface regions. So this upward or upwelling motion of hot gas does not operate, because the magnetic field itself prevents that upward motion. And because the upward motion is not effective, then the gas itself does not warm up, and then we have a cold spot, sunspot, cold spot. So strong magnetic fields associated. So yesterday I showed a video of coronal mass ejection. It's a fantastic display of energy and solar mass loss, and is also associated with magnetic fields.
And it studies the magnetic structures which emerge through the photosphere, or the visible surface of the sun. The Genesis spacecraft collected samples of the solar wind, a stream of charged particles from the sun. The samples were returned to Earth in 2004 and are now being studied in a special lab at NASA's Johnson Space Center. STEREO, which launched in 2006, uses two observatories, one ahead of the Earth in its orbit and one behind, to study the structure and evolution of solar storms.
Sorry, my connection is not ideal here.
As they blast from the sun and move out through space. SOHO, the Solar and Heliospheric Observatory, has been keeping a watch on the sun since 1996. It can warn the Earth of approaching.
Yeah, I think I stopped the video. Bad connection here. Sorry about that.
Coronal mass ejections that could disrupt communications.
Yeah, sorry, lady.
Never look directly at the sun, or you might damage your eyes.
So let's take a look and browse through chapter 16, in which emphasize the sun as a powerhouse, basically we are going to follow energy since its production in the core to the point that energy leaves the solar atmosphere. So conservation of energy is one of the important aspects of physics when we learn physics, and that is energy is a quantity, a measurable quantity that it is conserved and you can account for all its lost. Like money, for instance, when in the beginning of a month, let's say you have a paycheck and you have a certain amount of money there, and throughout the month, or perhaps in a few days, all that money is gone. So you can go back and figure out what was your intake or income throughout the year and what all your losses were. So money does not disappear. I mean, you can budget to the point that you find the exact amount of cents used here and there, and so there is no cent that cannot be not accounted. So same thing with energy. So if you think about energy, once some energy is produced somehow, that energy is going to be used to do things, and at the end of a cycle, you can account for the amount of energy used, the amount of energy gained during the process, and you can budget that. So in other words, if the sun has the ability of producing energy in its very central part, that energy does not disappear. That energy is used up during the process of moving outward to the solar atmosphere and is used up by warming up the interior regions, by keeping the sun stable, by allowing the sun not contract to become a black hole, if you will, and so the sun has experienced some stability since the moment it was formed at about 4.5, 4.6 billion years ago, and has been going on since then. Now, this production of energy, as we will see, requires the fusion reactions of hydrogen into helium, and the sun has passed uh, more than half of its core, or more than half of its hydrogen in the core has already been converted into helium. So the sun has a finite life, if you will. So another few billion years, and that supply of hydrogen in the core will be depleted. And when this moment arrives, then the sun will experience the next stage in its evolution. So the sun will stop being what we call main sequence to be something else, to be a different type of star. So mass, according to modern physics, mass, as we call kilograms, for instance, mass is in fact some sort of energy. So any particle like electrons, protons, neutrons that we studied previously, they can, under certain circumstances, always associated with very high temperature, these particles can be converted into radiation, into light, if you will, into energetic light, more particularly gamma rays. So in situations where the temperature, the environmental temperature is very high, um, uh, pairs of electrons and positrons, which are positive electrons, can be created out of a pure gamma rays. And they can combine again to produce light. So you can get electrons and positrons being merged and generated in their turn gamma rays. Same with protons and antiprotons. So when you merge these particles together, you produce light, matter and antimatter. So according to modern physics, so everything you see around yourself is a bottle up of crystallized energy or radiation. And you can quantify that with this simple expression that Einstein came up in the beginning of the 20th century, that energy is equivalent to mass times uh, uh, the square of speed of light. And that is certain amount of energy that we can use to do things. Now, if physicists they take four atoms of hydrogen and they squeeze them with the use of high energy to the point of creating an atom of helium, the atom of helium is slightly less massive than the atom of four, the mass of four atoms of hydrogen. Let me explain again. So if we take, see if I have the equation here. If I take the mass of four protons, which is the equivalent of four atoms of hydrogen, if I take the mass of four protons, which means four hydrogen, and you squeeze that using an environment with a large energy, the resulting process might lead to the formation of one atom of helium that has two protons and two neutrons and two electrons too. But electrons are not that massive. But when you compare the mass of this resulting helium with the mass of four atoms of hydrogen, the mass of helium atoms is slightly less. So that that excess, that lost mass, was in fact converted into energy in this process we call fusion reactions. And that energy is what is right now making my room very hot. Part of it is the energy that light up the sun, is the energy that light up the solar system. So this is a schematic of an atom of a nucleus. So you have certain particles here in a fusion reactions. You fuse them, you merge them, you create something heavier. In the case of the sun, there are specific steps by which protons are merged to create helium atoms. So if you take two atoms of hydrogen, you are going to, as a result, produce a neutrino, um, a deuterium, which is an isotope of hydrogen, and a positron. Okay. Now, if this reaction keeps going and the deuterium fuses with another hydrogen, then you have a helium 3 atom being formed, plus gamma ray, which is radiation and energy. And then when you take this third step and you fuse these two helium-3 atoms, you ended up back with two atoms of hydrogen, but you have a newly formed atom of helium. So this chain, this pp chain, proton-proton, or pp chain, what you need to memorize for as far as exams, as far as your assessment is concerned, is that in the core of the sun, four atoms of hydrogen are squeezed and fused together to produce one atom of helium plus particles named neutrino that escapes without interacting with the rest of the sun, plus gamma rays, plus energy. And that gamma rays, this energy, gets trapped in the solar interior and is used up to warm up the solar outer shells. And here's the calculation. So if you take four atoms of hydrogen, that's the equivalent mass of it. And if you take the equivalent mass of a helium atom, you have much less than that. Okay. The sun is a stable star, and at any given point, and I think we mentioned this previously, the sun is a star that is under what we call hydrostatic equilibrium. Hydrostatic equilibrium. This is an important term. So hydrostatic equilibrium means The sun is not contracting like a young star, and the sun is not expanding like an old star dying. The sun has kept the same volume for a very long time, and because of this stability, because of this balance between gravity that try to pull the sun in and the energy that attempts to be released as it is produced in the core. So because there is a balance between those two agents, the inward force of gravity and the outward force derived by gas pressure eventually, because there is this balance, the sun is stable. And its stability has been very good for us. I mean, life here on Earth developed the way we know because of that stability. Take a look at what's going on now as far as global warming is concerned. I mean, I mentioned this before. Earth in the past has been hotter, much hotter than it is now, has been much more concentrated. Carbon dioxide has been more concentrated in the atmosphere in the past than has been now. Now we are dealing with 400 parts per million of carbon dioxide, but Earth has gone to over 1,000 parts per million of carbon dioxide in the atmosphere, but life was thriving. And the reason for that is uh, Earth reached that level of high temperature and or high concentration of carbon dioxide over a very long period of time. So what life doesn't like is abrupt changes. So when this change occur in a mild way, in a very progressive way, everybody's happy. But when changes occur in a short time, everybody's unhappy, and life doesn't like that. It's too much confusing. So right now, uh, the effects of this quick change in temperature can be seen in our California with all this fire that going on with these heat waves that is affecting our land so effectively. So going back to the sun, the fact that the sun has this hydrostatic equilibrium, it has allowed for a mild change in its flux output that has in its terms slightly changed the conditions here on Earth, but over a long period of time. That's the convection zone, the solar interior, and I already mentioned that before. And that is a profile of our solar interior. Okay, so those are the important issues to be addressed in this today's chapter. Tomorrow we are going to be tackling stellar properties, and we are entering the realm of stars. Sun is a star, but it's a close star. We can have a close view to it. But tomorrow we are going to learn the techniques astronomers use to infer the stellar properties, metallicity, rotation, speeds and motion, all of that just by using the two basic tools of astronomers, photometry and spectroscopy. Okay, good night to all of you.